Welcome everyone to another Math and High Energy Physics seminar. Today we are honored to have Professor Zohar Komargodski from Simon Center for Geometry and Physics to present an overview of the Chern-Simons interaction, classical and quantum. During the session, if you have any question, please use the raise hand feature. And I'm happy to hand over the session to Zohar right now.
My plan for today, I wasn't exactly sure what's the level that's expected from this lecture, but I assume something like a graduate introductory graduate class.
Yeah.
To gauge my level. So I'm going to tell you a little bit about the classical physics of the Chern-Simons interaction and then the quantum physics. And we'll get even to quantum field theory and some more advanced, very recent developments, just to cover some recent developments in the field. So, okay, let's start. So, of course, I'll just start by reminding you that for the Maxwell equations, which describe the propagation of electric and magnetic fields in space-time, one of the main features is that there are solutions in free space, even in space where no density or current is present. There are interesting solutions. These are the electromagnetic waves, which move at the speed of light. And famously, there are two polarizations for the electromagnetic waves. You can choose various famous bases for these polarizations, like linear polarizations or circular polarizations. And this is a famous fact from 3+1 dimensional electromagnetism. Now, if you go to 2+1 dimensions, so namely in two space dimensions, a priori, the situation is not very different. So let's go over the differences in 2+1 dimensions. So one difference is that the magnetic field doesn't have an arrow anymore. So the magnetic field becomes a scalar field in 2+1 dimensions, because if you remember in electromagnetism, the electric and magnetic fields are derived from the field strength tensor F mu. The electric field comes from the components which are mixed space and time, and the magnetic field comes from the pure space-space components. But in 2+1 dimensions, there is only one space-space component. So the magnetic field is essentially a scalar. More precisely, you can think of it as a pseudoscalar. So it's just an object with no arrow. It doesn't have an arrow, unlike 3+1 dimensions. Another thing is that I have to define what is the notion of a curl. So this kind of product you're familiar with in 3+1 dimensions. In 2+1 dimensions, it works very similarly, but there is a convenient notation that I will use for a couple of slides, which is this. If you take any vector Vx, Vy, you can construct a dual vector V with a twiddle, where you take the Y component, put it first, and then you negative the X component and put it second. So that's called, let's call that a dual vector in two space dimensions. It will be a convenient notation for defining a notion of a curl. And we can do this operation with putting a twiddle on the gradient operator and on the electric field, etc. So how do the Maxwell equations look in 2+1 space-time dimensions, or two space dimensions? Well, the first equation is the Gauss law. It's the same as in 3+1. This is the analog of the curl equation for the electric field, and that's the analog for the curl equation for the magnetic field. And these are the Maxwell equations in 2+1 dimensions. So there is a current, there is a density, and there is some... So we see that instead of 4 equations, we only have 3 equations. So if you just compare the two slides, we see that we have lost one equation. When we go from 3+1 to 4+1, from 3+1 to 2+1, we have essentially lost this equation, that the magnetic field is divergenceless. And that's because the magnetic field is no longer a vector, as I said. So we have 3 equations, and the phenomenology of electromagnetic waves is very similar to what you've learned in undergrad. The only difference is that instead of 2 polarizations, there is now only 1 polarization. So an electromagnetic wave would be traveling in some direction. There will be an electric field that's transverse to it, and there will be a magnetic field that's just a scalar function. And there is only one polarization. And as before, the electric field is transverse to the direction of the propagation, as in 3+1 dimensions. So far, it's very simple. All you have to remember is that the phenomenology in 2+1 dimensions of the Maxwell equations is that they describe only one polarization moving at the speed of light, unlike the situation in 3+1 dimensions where there are two polarizations. Are there any questions about it? Okay. Now, the deep physics begins in this slide. That's where something very unexpected is starting to happen. And this thing influenced physics for the last 4 decades at the very least. It's a very important fact to know. It turns out that unlike in 3+1 dimensions, where the Maxwell equations are extremely robust, and they can essentially not be modified in any interesting way. You can, of course, introduce dielectrics and this mu and epsilon functions, but in vacuum, they cannot be modified in any sensible way. In 2+1 dimensions, there is a modification of the equations, which is relativistically invariant. It's consistent with all the symmetries, and it looks very natural. And that's the Chern-Simons That's the Chern-Simons modification. Okay, so we look at the 3 equations, and suddenly in the Gauss law, there is another contribution coming from the magnetic field scalar function with a new coefficient kappa. So kappa is a new free coefficient, which is related to the Chern-Simons coupling, which I will review soon. This equation is not modified. That's the equation that says that there is an electromotive force when you change the magnetic field through some solenoid. While this equation is modified, again, there is some new term here. So we see that there is a consistent modification compatible with Lorentz invariance, and that's not possible in 3+1 dimensions. You can try, but you will not succeed. That's the claim in 3+1 dimensions. Okay, so my purpose is to first investigate the classical ramifications of these surprising modifications of the Maxwell equations in 2+1 dimensions, and then go to the quantum theory of what to do with this modification. Are there any questions about it? Okay.
Excuse me.
Yes.
Yes, sorry. Is that the most general modification you can add? Couldn't you add, for instance, some nonlinear terms in E or in the B fields, for instance?
Yeah. So when I said that the Maxwell equations in 3+1 dimensions are robust, what I meant really is that I'm interested in modifications which are linear in the fields and perhaps at most first order in derivatives. Just not to, I mean, if you open the door for completely general modifications which are potentially nonlinear in the fields and have more derivatives, then there are many modifications in 3+1 dimensions as well. But what is the physical reason to doing that? We want a modification that will influence the physics at long distances very dramatically. Otherwise, it's kind of not very important in the infrared, okay? So for that, you have to have few derivatives because modifications with many derivatives will die out at low frequency and at low frequency and large wavelengths. And modifications which are nonlinear in the fields will die out for small field amplitudes. So this modification here is much more dramatic because it really influences the propagation of waves at very low frequency and large wavelength and across long distances. So it's a very dramatic modification. So to be precise, you could say that in 3+1 dimensions, there is no dramatic modifications. There are no dramatic modifications, only modifications that don't influence the long distance theory. While here, there is a modification that influences the long distance theory. Is that okay?
Yes, thank you.
Okay, so we will investigate this modification now. So in the math literature, this kind of modification arose in the work of Chern and Simons from some differential geometry story, that will be tangential to what I'm talking about, so I'm not going to get into it. But in the physics literature, this modification, as far as I know, was first studied by Deser and Jakiv and Templeton as an interesting modification of electrodynamics. And that's more in line with what I'm presenting. So I'll be presenting the story more in line with that logic, but we will deviate very soon when we go to the quantum theory. So let's try to understand the phenomenology of these Maxwell equations. Let's call them Chern-Simons Maxwell equations, just to be concrete. It's a very simple exercise you could do on your own, obviously. These are linear differential equations. You can solve them on your own, but I'm just going to tell you the answers. So we can ask what happens when you put a source. So remember that in the ordinary story, if you put a source, you get a Coulomb field. Here, it turns out that when you put a source and you try to solve those equations, you'll get that the electric field is exponentially decaying. So you have lost the long-range nature of the electromagnetic field. So that's a testament to what I said before, which is that it affects the long-distance theory dramatically. So you have lost the long-distance nature of the Coulomb field, and now it's decaying exponentially. That's comment number one. Comment number two, there are some waves which exist in space without sources, as before, but those waves are not moving at the speed of light anymore. Those waves are moving like those waves will be moving at a speed which is smaller than the speed of light. The waves in that theory will be behaving as if these are waves of a massive field rather than a massless field. So they will obey this dispersion relation of a massive particle rather than a massless particle. So we have lost the Coulomb force and we have lost the speed of light, the propagation at the speed of light. These are first two comments. An interesting fact that must not be overlooked is what happens when you put a static charge Q. So in the ordinary theory of Maxwell, we get a Coulomb field, but we don't get any magnetic field, obviously, because we haven't introduced magnetic monopoles. But with the Chern-Simons interaction, you can look at these equations. You will see that when you put an electric source, you are going to source a magnetic field as well, and not just an electric field. And indeed, this kind of point charge sources not just an electric field, but also a magnetic field. And the magnetic field also decays exponentially away from the charge. And if you want to be precise, instead of just putting squiggles, these are the actual solutions of the equations. So the electric field goes like the first Bessel function, and the magnetic field goes like the zeroth Bessel function. And the electric field at very short distances looks like a Coulomb field. So at very short distances, this Chern-Simons Maxwell theory, if you're very close to the source, it behaves like Maxwell's theory at very short distances. You get a Coulomb field from this equation. But when you go to very long distances, it decays exponentially. The magnetic field diverges logarithmically at short distances, while the electric field diverges linearly at short distances. But both of them decay exponentially at long distances. Are there any questions about the phenomenology of this theory?
Someone asked, so how is the wave equation modified?
Let me see. Is that in the chat?
Yes.
Oh, I see. How is the wave equation modified? This is how the wave equation is modified. If you want to understand waves without sources, you have to put rho and j to 0 and sit at home and solve these differential equations, and you'll find waves that move at a speed which is smaller than the speed of light. That's my claim. The second claim I made is that if you have a point source, it leads to deviations from what you know. The electric field decays exponentially at long distances. It's still Coulomb at short distances, and there is also a magnetic field that decays exponentially. This is for a static source. And here I've plotted them for you. So here it's Coulomb-like. It diverges very quickly. The magnetic field diverges much slower, but they both decay exponentially. Okay, so these are the basic properties of Chern-Simons Maxwell theory, which is a classical field theory. Any more questions about it? These are very important points. If you haven't seen this before, this might look shocking that such a theory exists.
A quick question. I imagine that you will probably comment on this later. But once you quantize this in theory, do you produce like a massive kind of photon?
Well, the theory has a massive particle classically. You don't need to quantize anything. If you just look at the differential equations and you put the sources to 0, you will find that this theory has waves, very much like the same waves as in Maxwell's theory. But the waves are not moving at the speed of light. So they obey a dispersion relation of a massive particle. I can write it in the chat. So they obey the dispersion relation omega squared equals p squared plus m squared. And m squared is going to be proportional to k squared. To kappa squared, where by k I mean kappa. So it's just a classical filter that this classical filter has a massive particle. You don't need to quantize anything. It's of course not a fundamental particle. When you quantize, waves become fundamental particles, right? We have electromagnetic waves, and when we quantize, they become fundamental photons. And they become like unbreakable quanta. So something similar will happen when we quantize this theory, that these massive electromagnetic waves will become elementary massive particles. Maybe that's what you were asking.
Yes, that was exactly my question. Thank you.
Yes. Any more? Okay, let's keep going.
Could clarify his question a little bit in the chat. Like, of course, says maybe it's second derivative.
Is the massive nature related to the symmetry of space? One interesting thing about this modification that I already emphasized is that it's completely Lorentz invariant. So ab initio, there is no real difference between the symmetries of this equation and the symmetries of the equations without the Chern-Simons modification. If you want to be super pedantic, just for a second, there is a tiny difference, which is that these equations admit, in addition to Lorentz invariance, also parity, while these equations break parity. Why? Because, how do you see that these equations break parity? I mentioned very briefly that the magnetic field in 2 + 1 dimensions is a pseudoscalar, but the divergence of the electric field is a scalar. So you're adding a scalar with a pseudoscalar, and that means that the coupling constant kappa is actually parity odd. So these equations are Lorentz invariant, but they're parity odd. And maybe the reason that you have not seen it in undergrad is because most of the physics that we see in daily life is parity even. So to look to situations where the Chern-Simons interaction arises are somewhat rare because they require the breaking of parity symmetry. So that is a sociological explanation for why you have not studied it in your undergrad, perhaps. Because these equations are Lorentz invariant, but parity non-preserving. Okay. Okay. Now let's get to let's keep digging. We keep digging in the classical theory, not yet quantum. A very important question is to understand, why do these static sources produce a magnetic field? We see that they produce a magnetic field. It's this Bessel function that it decays exponentially. But you can ask, how much magnetic field do they produce? So you can ask, what's the area under this curve appropriately normalized? That's like asking, how much is the total magnetic flux that is produced by inserting a single electric particle? So we are inserting an electric particle, but it produces a magnetic flux. And you can just use your Stokes theorem or whatever it's called, maybe Gauss law. You can use the Gauss law, integrate this equation, use the fact that the electric field decays exponentially to drop this term, and you'll find that the total magnetic field through the whole space is Q over K, over kappa. Kappa is the Chern-Simons coupling. It's a new fundamental constant. And Q is the charge of the little piece of charge that we put in the middle here. Okay, so we have some magnetic field. That's just very nice formula for the total flux of the magnetic field. Okay, you must remember that. If there is something to remember, is this formula. Just please print it in your brain. Okay, in the classical theory, kappa could be any number. It could be even 1 over pi. And there is not much to say about what are the allowed values of kappa. However, in the quantum theory, this fact that these point charges produce a magnetic flux will become very important. That will be the hero of the story that we're going to talk about throughout the remaining of this lecture. It's about the quantum theory. And then the question of what are the allowed values of kappa and what does it do will become essential. One way to think about it, if you like, is that you can think that every point particle which has electric charge becomes essentially a little solenoid. In condensed matter, they call this phenomenon a flux attachment, that each electric particle is now like joined by a little solenoid that travels with it. The solenoid is this magnetic field that's produced by this particle. And why is it interesting to go to the quantum theory? Why are we even trying to go to the quantum theory? Because you probably remember from your undergrad that solenoids lead to very interesting long-range effects in quantum theory. So in the classical theory, this theory is maybe slightly boring because everything decays exponentially. There is no long-range forces, but the quantum theory here has long-range forces. And that's the key physical idea, that classically there are no long-range effects, but quantum mechanically there are long-range effects. And why is that? It's because of the solenoid. We know from quantum theory that solenoids can produce long-range effects, and it's a purely quantum effect that's known as the Aharonov-Bohm effect. Are there any questions about this philosophy of why we're trying to investigate the quantum theory? Okay. So this is the picture. We're now, let me see how I'm doing with time. Okay, looks good. So this is the picture. We just imagine putting point charges which are very massive. These point charges are like heavy nuclei. They're not moving anywhere. It's like a lattice of a solid, you can think. But because of the Chern-Simons interaction, each one of them produces a magnetic field, which is very localized to the vicinity of the charge, right? We discussed many times that the magnetic field decays exponentially away from the charge. So it's mostly localized at the blue dot. And it's the value of this magnetic flux is Q over kappa, sorry. And I drew an arrow for the magnetic field because, you know, space is three-dimensional and physical realizations of the Chern-Simons interaction are on a plane inside 3 dimensions. So the magnetic field on the plane is a scalar, or more precisely a pseudoscalar, but physically, of course, it's an arrow that's pointing out of the plane. That's a transverse magnetic field. So this is the picture that we have these point charges. Classically, they don't talk to each other because everything decays exponentially. But quantum mechanically, they are going to see each other through the subtle effects of quantum interference. Okay? Let me see if there are. Good. So this is the picture. Now I'm going to remind you about why solenoids lead to long-range quantum effects, even though classically they are very innocuous. So quantum mechanically, solenoids which carry some magnetic flux through them, this is the blue circle here, they're very important because when electrons go around one way versus the other way, you get some modification of the double slit experiment. So we know that there is this famous interference in the double slit experiment that I'm not going to review. But if you further put a solenoid, it changes the interference pattern because the phase that's accumulated by going one way versus the other way changes due to the solenoid. This is the very famous Aharonov-Bohm effect. And here is like a depiction of what's going on. When you put a solenoid, you get some displacement of the interference pattern. So you do the double slit experiment with a solenoid, and you can see that if the original pattern was this dashed line, after you put some flux through the solenoid, your actual pattern might be shifted. So that's the long-range effect of a magnetic field that's localized into a solenoid. This is some classic stuff from 70 years ago. I'm just reminding you of that. Just a second. I have some little hiccup here. Okay. So let's understand the solenoids. Let me just review the effect of these solenoids in the double slit experiment, and then we will apply it for this Chern-Simons business. So we ask, what is the magnetic field inside the solenoid? And it could be any number. But if this number is 2 pi over the elementary charge times an integer, E is the elementary charge. It doesn't have to be the charge that we put in that sample. Remember that picture? We put Q. That could be some nucleus with some integer multiple of the fundamental charge E. So by E, I mean the fundamental charge. So if the solenoid flux is 2 pi over E times an integer, any integer, positive or negative, then the solenoid becomes invisible. And the interference pattern in the double slit experiment is the same as the original pattern. But if the magnetic flux is any other number, that's not 2 pi over E times an integer, then the solenoid becomes visible. And the additional phase that you accrue going one way versus the other way is the exponential of I times the fundamental charge times the flux. So you see, that's why this condition that's why this is the correct equation. Because if this condition is satisfied and you plug it here, then you get that the phase is 2 pi I times an integer. So it's gonna be just trivial. Otherwise, the phase is non-trivial. Is that clear? Any questions about it? Okay. The Aharonov-Bohm thing is a little weird because some people learn about it in undergrad, some people don't. Okay. Now, just for simplicity, I'm going to assume that the charge that we put in our two-dimensional sheet, we have this two-dimensional sheet, and we're going to put the fundamental charge. So each of the Q's will be just E, just for the simplicity of calculations. Then, while classically nothing was going on, everything was decaying exponentially, the wave function of this nuclei, now imagine writing a wave function. This could be some heavy nuclei, they're moving very slow, and we try to write a wave function, then quantum mechanically, the wave function cannot be single valued, which is an exotic fact. Because every time two nuclei go around each other, they have to accrue a phase. So we get a deviation from what you learned in school, which is that wave functions have to be either symmetric or anti-symmetric. So you learned in school that wave functions have to be symmetric for bosons and anti-symmetric for fermions. That is correct, but it's just a small piece of the story. What actually is going on is that every time a coordinate of one of the external charges goes around the coordinate of another one, the wave function picks up this particular phase. E to the 1 over h bar i.e. integral of b. I'm sorry, here I forgot to put h bar. I apologize. There has to be an h bar in the numerator here, and there has to be an h bar in the denominator here. So the actual phase that the wave function picks up is 1 over h bar i.e. b. And now we have to remember the formula that I told you to put in your head, which is that the total magnetic flux that's carried by a particle is Q over kappa, which for Q equals E is equal to E over kappa. So I just multiply this by E over kappa, I get E squared over h bar kappa. So the wave function is neither symmetric nor anti-symmetric, and you were lied to in school. This is the phase that the wave function picks when coordinates go around another coordinate. And how do we call it? We have to invent a new name because we have bosons and fermions, which correspond to symmetric and anti-symmetric wave functions, but this is called anyons. So this is a generalization of bosons and fermions. which is essentially particles with this particular symmetry property of the wave function. You can say that you want to call it spin. You can call it spin because the wave function is anti-symmetric for spin a half, and the wave function is symmetric for integer spin. You can say that these particles carry fractional spin, and this is the fractional spin, e squared over 4 pi h bar kappa. And you can say that that's why the wave function is that has this multi-valued structure, and it generalizes the usual statistics of fermions and bosons. In the particular case that this exponent is I pi, we just get maybe, in some particular cases that we'll discuss, this exponent is 1, and this reduces to fermions or bosons, and the spin is a half or 1. So if this spin is a half, we get fermions. If this spin is 1 or 0, we get bosons, or any integer. But it generalizes this notion to anyons, to more general particles, which are neither bosons nor fermions. So you see that the quantum theory leads to anyons, and that's the first conclusion of this discussion. The Chern-Simons term leads to anyons. Are there any questions about it? Okay. So I guess people are not terribly surprised that you can go beyond the statistics of bosons and fermions. Let's keep going then. By the way, the Schrödinger problem with this particular, you remember that there is an ansatz to solve the Schrödinger problem for anti-symmetric wave functions, which is the Slater determinant. Here, there is no ansatz like that. With this kind of statistics, nobody has invented a smart ansatz to solve for the wave functions. And mostly people find wave functions of anyons by computer work. They just put it on the computer and ask for the computer to look for these multi-valued wave functions with some very sophisticated algorithms. We don't know really how to solve this kind of Schrödinger problems. Even for free particles, by the way, without any interactions. It's very difficult. Okay. Let me just check that there are no questions in the chat. Okay. Okay, so I'm printing again the formula for the spin. And here comes something that is very difficult to explain without going into very many technicalities, which is you can ask the following question. In the classical theory, we know that kappa could be anything. So the spin could be anything, and this phase of the anyons could be anything. Are there any constraints in the quantum theory? That's a legitimate question to ask. And the answer is yes, there are constraints, but they're very difficult to derive. So in the quantum theory, it turns out that this kappa cannot be anything you want. It has to be e squared over 2 pi h bar times an integer. And therefore, if you plug it into this formula and you calculate what are the allowed spins, effective spins for these anyons, you see that the effective allowed spins are 1 over 2n. This is mod. So in particular, n equals 1 corresponds to a fermion, and n equals infinity corresponds to a boson. Okay, I should have probably added it on the slides, but I'll write it in the chat. N equals 1 is a fermion, n equals infinity is a boson. Okay, and you get anything in between. You can get you can get like this 1 over 2 and many numbers in between. Okay, so the derivation of the fact that kappa has to be quantized in this particular way is very difficult, and I won't be able to explain it to you very clearly. I can spend a minute trying to give you a qualitative argument for the more advanced students. And if there are questions about it, maybe I can try to sharpen it. So what is the best argument that I know? So the best argument that I know for this quantization is to consider this two-dimensional sample. And imagine that you're required on physical grounds that you want to be able to put this sample in a compact space. So like something like a torus. So you could imagine that your sheet is a torus or a donut. And now the total magnetic flux through this donut would be Q over kappa times the number of particles, because each one gives you Q over kappa. there is a theorem in mathematics that the total magnetic flux has to be an integer through compact manifolds. That's one of the Chern classes. So if you require that Q over kappa is an integer, you can see that this roughly speaking leads to what you want. Because if kappa would not be an integer, then Q over kappa times an integer would never be 1. So roughly speaking, you can say that this comes from requiring that the theory makes sense in compact space. That's what I wrote here. Roughly speaking, you can say that physically we require that the theory would make sense in compact space, and that's why we get this quantization condition quantum mechanically. Classically, it's not constrained kappa. Okay. Any questions about it before I keep going? Okay.
So it's forbidden to have spin 1 particle in the theory.
No, it's not forbidden. I was just a little bit too glib. You see, when you know the properties of the monodromy, what I said here is that this is the phase that is picked by the wave function when x1 goes around x2. If you want to use the notion of spin, remember that spin 1 is a boson, spin 2 is a boson, spin 3 is a boson. So they all have symmetric wave functions. So when I wrote the spin here, this is the fractional part of the spin. So if you want to be super precise, the actual spin is this formula plus an integer. Because when you take a fermion and add the integer spin, the wave function is still antisymmetric under the interchange of 2 coordinates. So that's not going to be changed. So really the actual physical spin is not that. That's the fractional part of the spin. In the Chern-Simons literature, it's called the topological spin. Really, you need to add an integer here. So this spin is just the fractional piece. And it's up to an integer. But it's an excellent question. So you can get any number which is an integer plus 1 over 2n from this theory. Any other questions? Okay. So you can ask, is this all science fiction or not? And of course, you know the answer. These two-dimensional sheets with particles that behave like little solenoids and with these bizarre wave functions which are multi-valued does arise in nature. It arises in nature in several situations. It arises in graphene, which is like a recent development. It also, I mean, in bilayer graphene, for instance, which was shown recently. But more traditionally, if you look at textbooks, it arises in the problem of starting from ordinary electrons of spin 1/2 in a very strong magnetic field. It turns out that the low energy effective field theory, because it breaks parity due to the magnetic field, has this Chern-Simons interaction, and there are anyons. And this was already demonstrated in experiment very decisively, and people got Nobel Prizes for it. So we know that this is part of nature. I mean, we know that this thing can occur in nature, and there are several situations where this physics can be found in experiment by now. So there is the quantum Hall effect, there is some bilayer graphene story, and maybe some others. I'll get to a few others later in the slides. Okay, so this is not science fiction. These anyons do exist, and these multi-valued wave functions do exist. Okay, one reason that a lot of people are extremely excited about anyons, and there are literally thousands of papers about it every year, is that anyons are believed to be a key to quantum computations. And that there is a specific even code which has anyons, and they can be manipulated and can be viewed as a toy model for a quantum computer. That's the famous Kitaev surface code. It's a very concrete implementation that has anyons, which can be manipulated very conveniently. Why is that so important for quantum computers? Maybe somebody in the audience want to say? Why is this like, instead, somebody has some idea, or should I say? So the reason that it's believed to be crucial for quantum computers, something like that, is because the long-range interaction here is very robust. It's like, even if there are some interactions with the environment, maybe the environment can, like damage some stuff that's local in one of the charges, but this long-range interaction, which is through the total magnetic flux, and since the magnetic flux is quantized, is really not something that you can easily destroy. So because this long-range interaction is so robust, it's believed to be quite stable against coupling to the environment. And so this allows you to create some effective quantum variables that you can manipulate without being too worried about the environment. Of course, you still have to do error correction because there are still some environmental effects. But as a starting point, it's a very promising starting point. And you can see that the quantum gate essentially takes two of these charged particles. These are in this beautiful picture, and it starts moving them, like braiding them across each other. You see there is a braid that leads to some phase, and this phase is believed to be very robust to environmental effects. Okay, so there is a huge amount of excitement about these anyons in the quantum computation community, in the quantum computers community. Okay. Now we get to the most challenging part of the talk. I'll just give the introduction and we'll take a break maybe. So far, we discussed anyons in the way that are most interesting to quantum computers at the moment. At the moment, when we discuss quantum computers, we have heavy anyons. This could be some nuclei or big atoms. And we braid them, we get a phase, and this phase is used as a quantum gate for some quantum computation. In this phase of matter, the anyons are very heavy particles. We can just manipulate them like heavy nuclei. They carry this magnetic field and they behave like heavy nuclei, for instance. A very interesting question is what happens if these anyons can be created from the vacuum? So this is a regime. So more, if you want to be super precise, how do we make the theory of anyons quantum, but also relativistically invariant? So if you go back in the slides, all these things that I told you used quantum mechanics, non-relativistic quantum mechanics of the Aronoff-Bohm flux. And we treated anyons as heavy particles. An interesting question is, how do we make anyons relativistically invariant? So these are relativistic particles. And what are the quantum effects that come from creating anyons, anti-anyon pairs from the vacuum? So a photon could propagate and two anyon, anti-anyon pair could be created from the vacuum. What are the effects of such loop diagrams? That's the question. This is not a regime that is very interesting to quantum computers now, because the anyons are heavy and you want to manipulate them without creating them from the vacuum. But we must investigate the various phases of anyon physics. We might find lots of interesting things. It's a curiosity-driven research of what happens when anyons become dynamical rather than just heavy external particles. So that's what we're going to do after the break. We'll study what happens when anyons become dynamical. Okay, so there are 3 questions, all excellent in the chat. I'll go over them one by one. We'll take some of them are worthwhile to spend a few minutes on. So first question is that there is no Lorentz group representation for anyons. How can anyons exist or be coupled to photons? Well, first of all, if you look at the Maxwell-Chern-Simons equations, these are Lorentz invariant equations, and the anyons are sources. So far, we did not quantize the sources, right? We just view the sources as classical sources, and we analyzed the magnetic field that they carry, and then we did some kind of first quantized description as if the sources are just very heavy particles. Now, the question is whether the sources can be made relativistically invariant. And the answer is, well, yes, that's what I'm going to explain. The sources can be made relativistically invariant. So we can create the anyons and anti-anyons from the vacuum. And we will couple the sources to the Chern-Simons Maxwell gauge field like A dot J, like we always do. So I hope this addresses the first question, that it is possible. Yeah, it's true. These are not going to be spinors. Yeah, these are going to be some other things. They're not going to be spinors. Okay, next question. Why the wave function became multi-valued? Okay, this is a very important point. So we imagine the wave function of, let's say, 6 nuclei, like in this picture. And we want to understand what happens when we take, let's say, this black one, and we drag its coordinate all the way around this one. So not crossing anybody else, like, let's say, this kind of trajectory. And we want to ask what happens to the wave function. So this is like taking a charged particle around a solenoid. And we use the fact that we know that when we take something around a solenoid, it leads to a phase. And the phase is the exponential of IE times the total magnetic field divided by H bar. So then we plug the total magnetic field that's carried by each of these solenoids, and we get a phase. So I hope this is sufficient as an explanation of why the wave function is multi-valued. I'm not sure it's sufficient, but I just repeated what I said. Now, in 3+1 dimensions, another question is that in 3+1 dimensions, there is a modification of the Maxwell theory, which is to add a Higgs field like we do in superconductors. And that way we give the photon a mass. And then all the localized charges decay exponentially. This is an excellent comment. I'll say two things about it. First of all, this mechanism of giving a mass to the photon does not involve adding more degrees of freedom. That's a very, very important deep point. So let's review how the superconductor works, or in more familiar language, how does the U1 plus Higgs field works. So we start from two polarizations. We add the Higgs field. The gauge field eats one of the components. And then at the end of the day, we have 3 massive components versus 2 massless components. So we have 3 massive components for the spin 1 vector photon plus the Higgs particle. Let's ignore it. But we went from 2 massless polarizations to 3 massive polarizations. That's how the Higgs mechanism works. Ignoring the Higgs particle for a second, it could be very heavy. In Chern-Simons Maxwell, it's completely different. We start from 1 polarization and we end up with 1 polarization. The polarization was massless and now it became massive. So it's a completely different mechanism. We're not increasing the number of degrees of freedom inside the gauge field. It just becomes massive on its own without eating the longitudinal, without eating the phase of a Higgs field. So there is also a Higgs field in 2+1 dimensions if you want. In some, it could be important, but that's not what we're discussing here. So here we don't have any Higgs field. It just happens on its own, so to speak. Okay. Any other questions? Okay, good. So let's investigate the theory of second quantized anyons, meaning anyons which are light, could be created from the vacuum, would be coupled to a photon. One could try to calculate loop diagrams like that. So this kind of family of quantum field theories, where the anyons are allowed to be created from the vacuum, leads to a huge generalization of quantum field theory. Sometimes these theories are called Chern-Simons matter-Maxwell theory. So it's a mouthful, or just Chern-Simons matter theories. So these are theories where there is this Chern-Simons business, plus the anyons are dynamical and not just probe particles like in the quantum computation setup. These are actual particles that can be created from the vacuum. So if the anyons are very heavy, you don't need quantum filter. You can use first quantization. Anyons are not created from the vacuum, and you can just go ahead and hammer the wave functions. You can try to solve for the wave functions. But when the anyons become dynamical, many interesting things start happening. First of all, the anyons can condense. So even though these are not bosons or fermions, they may condense. They can become gapless, massless. So even a theory with massless anyons is allowed. The anyons can become confined, and many, many other things can happen. We don't know everything that can happen. These are very difficult theories, but we know a little bit. So the story is kind of getting very rich when you try to study this kind of quantum field theories with dynamical anyons. So here I want to just quickly review what's the big picture here. If you look at the quantum field theory from, let's say, a very modern perspective, then there could be critical points, which are gapless. That could be some phase transition, but that could be some gapped phase, or it could be some symmetry breaking phase. And the gapless points, which are the conformal field theory points, are just second order phase transitions between some ordered phases and trivial phases. For instance, the Ising model, the massless CFT of the Ising model is a very simple example, well, a very well-known example of that. So we think about quantum field theory, massless quantum field theory, or quantum field theory with very light particles, as describing a phase transition between various massive gapped phases. And there is the Landau-Ginzburg paradigm, which says that this kind of second order transitions or conformal field theories should separate a trivial phase from an ordered phase. And that's a big paradigm in the theory of phase transitions. It's basically saying that we can detect ordered phases by like local order parameters. Now, in this theory of anyons violates the Landau-Ginzburg criterion. So what was the Landau-Ginzburg criterion? The Landau-Ginzburg criterion was that we have phases like liquid or like solid. So how do we detect a solid from a liquid? We detect a solid by an order parameter because the solid has a broken translational symmetry. So if we measure some local order parameter, like the expectation value of some operator with some typical momentum k, we will see that there is a solid structure. So solids are ordered phases. Magnets, the magnets that hang on your fridge, they're also ordered phases because they have spins. If you look with a microscope, you'll see that there are little spins, and all the spins are lined up in the same direction. So the Landau-Ginzburg idea from decades ago was that all the phases of matter are either completely disordered, completely featureless, or they have a local order parameter, like magnets or superconductors or solids and so on. Liquids, by the way, are not distinguishable from gases because you can continuously go from the liquid phase to the gas phase without any phase transition. And that goes along with the Landau-Ginzburg theory, because if there is no local order parameter that distinguishes them, then they should not be distinguishable. And the theory of Enyon just blew this whole logic out of its waters, I think the expression goes. Because the theory of Enyons is on the one hand non-trivial, it's ordered in some sense because there is this solenoid and there is this multi-valued wave function and people use it for quantum computation. So you cannot just say that the theory of anyons is trivial with nothing going on. On the other hand, there is no local order parameter because any classical local order parameter vanishes pretty much by definition because the whole effect comes from this long-range Aronoff-Bohm business, which is purely quantum, and it's not measurable by any local experiment. In fact, that's why it's so useful for quantum computation, because there is no local order parameter, so the interactions with the environment cannot destroy local order. the order is very non-local. In this phase of anyons, you can think that there is some order, but it's really hard to comprehend intuitively because it's very non-local. So it goes beyond the Landau-Ginzburg classification of phases of matter. And people invented a new name for that. They call it topological order. So you probably heard this word. It's a big buzzword nowadays. So it's not ordinary order, it's topological order. It's order that cannot be detected by the Landau-Ginzburg criterion, and it's a phase of its own. Okay, so we say that this theory of anyons is a topologically ordered phase. That's how you should say it in modern parlance. Okay, are there any questions about it? Okay. So the theory of anyons goes beyond the Landau-Ginzburg description. It's a topologically ordered phase. And now we have to start thinking. Now this allows me to motivate why am I interested in the theory of dynamical anyons? Because we have to generalize the Landau-Ginzburg picture, that there are trivially gapped phases like disordered magnets, and then there is an ordered phase like the ferromagnet, and there is a phase transition at the Curie point. So we have to go beyond this whole paradigm because we know that now there could be topologically ordered phases. And what are the phase transitions between topologically ordered phases? Because topologically ordered phases are when the anyons are heavy and there is this non-local order. But when the anyons become light and they can be created from the vacuum, maybe one topologically ordered phase can change to a different topologically ordered phase. So we have to start investigating phase transitions between topologically ordered phases. And that forces you to start thinking seriously about light anyons, dynamical anyons. So that's the motivation. So we'll do it in a toy example. I'm gonna cover in the next whatever remains from this from our time together. The simplest example that shows that there are phase transitions between topologically ordered phases. In those phase transitions, anyons become massless, and we're trying to make conjectures about the properties of those phase transitions. So we will study what you might call QED3. It's a three-dimensional theory of fermions, so we can write a Lagrangian, and people were complaining that you cannot write a Lagrangian for anyons. It is true. So we're going to use ordinary fermions instead, and there will be an F of them, an F species of fermions. But these fermions only look like fermions if you look at them. They look like ordinary spinors from the book, your favorite QFT book, maybe Peskin and Schroeder. But actually, inside this piece of the Lagrangian, there is a Chern-Simons term. So the actual excitations, if you hit the vacuum with a fermion, psi, you don't create an ordinary spinor. You create an anyon from the vacuum, and it will have all this funny braiding because of the solenoid magnetic flux. So that's how we write Lagrangians for anyons. We do use ordinary variables, but our kinetic term for the gauge field is not just F squared, it includes the Chern-Simons interaction. So this theory has some parameters. It has masses. These are the masses of our anyons. It has an F, which is the number of species of anyons. It has kappa, which is the Chern-Simons coupling that tells us how much magnetic field each anyon carries. And also it has a global symmetry, which rotates the anyons. It's a global isospin symmetry that just rotates the anyons into each other. Okay, so this is the Lagrangian, and you can do computations with this Lagrangian, at least in weakly coupled regimes. Are there any questions about it? Now I have to explain some little subtle point. So if there are questions about the big picture, ask now, because now I'm going to explain something a little subtle about the phase transitions between topological order. Okay, I see one question. Would it be correct to say that anyons arise from a pure gauge theory? I'm not sure exactly what to say. I'm gonna study the theory of fermions coupled to Maxwell and Chern-Simons. So I'll have fundamental fermions that became anyons because the Chern-Simons term makes them carry magnetic flux. And so in my theory, in QED3, the anyons did not come out of the blue. I pretty much put them in by hand. And when the anyons are very heavy, that produces to our discussion in the first half of the lecture. But we're going to try to investigate what happens when the anyons are light. Any more questions? Whether they can arise from some gauge theory without putting some extra matter? I think the answer is yes, but it's like I have to demonstrate it. It's not trivial, but I think the answer is yes. I think in some sufficiently complicated gauge theories, the gluons will become anyons. I'm pretty sure that's true. I just have to show you. To show you an example would take a lot of work. Okay. So Redlich, he's a famous physicist, discovered a very important subtlety, or a very important phenomenon, if you want. This is used throughout the literature. Redlich looked at this Lagrangian and said, oh, so when M is huge, I don't need second quantize, blah, blah. I can just think of the anyons are sources and just study their wave function. But Redlich realized something very deep, which is that it's very important whether the mass is huge and positive or huge and negative. If you calculate this diagram with huge positive mass versus you calculate the same diagram with huge negative mass, that's what Redlich did. You'll find that actually the topological order is not the same. So Redlich found that E over kappa, which is related to the how much magnetic flux is attached to each anyon. When M is huge and positive, that's the E over kappa. That's how much magnetic flux is attached to each anyon. But if M is huge and negative, that's how much magnetic flux is attached to each anyon. So you see that the shift in the denominator and the spin changes. The effective spin of the wave functions changes. So what Redlich did leads to remarkable implications. Redlich already showed that when the mass of these fermions psi goes from being huge and positive to huge and negative, if you do it adiabatically, topological order has to change discontinuously. Topological order is labeled by an integer, little n. And Redlich already told us that at huge positive M, you get one topological order with one type of solenoids, and huge negative mass, you get different topological order with different solenoids. And so Redlich already told us that there must be a phase transition as you change the sign of the mass. And the nature of this phase transition depends on the number of species, it depends on little n, but Redlich already essentially proved that there can be phase transitions between topological order and that they are very interesting. So here is my attempt to tell you what's going on. So when the mass is huge and positive, you get topological order labeled by the integer little n. When the mass is huge and negative, you get topological order labeled by the integer n minus nf, where nf is the number of species. And what happens in between, that's where there are dragons, okay? So we don't know. We don't have a good numerical algorithm that solves this quantum field theories of anyons with light anyons. That's when the mass is very small, okay? You can think about this region as zero mass for the anyons, when the anyons are very dynamical. We don't have a good numerical algorithm to understand how can there be a phase transition between these topological orders. So all we have to do is to use our quantum field theory tools like anomalies, symmetries, various conjectures about phase diagrams, duality, maybe supersymmetry, maybe even some insights for gauge gravity duality. You could stretch it and try to guess what happens. We do not have direct numerical algorithms that tell us the answers yet. Sometimes we have experiments. Amazingly, I'll show you some examples where experiment is available, and we believe that experiment will be useful in telling us what the answer is. But for now, for the most part, you have to think about it as a theoretical challenge. So where there are dragons, the anyons are massless, it's very strongly coupled, and we need to make conjectures or experiments. We cannot solve the theory directly because the theory of massless anyons is very strongly coupled. Okay, are there any questions about it? Okay. This phase transition, just to emphasize again, is clearly not Landau-Ginzburg type because it doesn't separate ordered from unordered phases like we have in magnets or in water, in liquid, I mean, or in helium-3 or superfluid, any other superfluid, or pretty much anything that ever people got a Nobel Prize for. This is a phase transition between two different topological orders, which are labeled by the long-range forces of the Aronoff bomb solenoids. So it's a very non-standard phase transition, and it goes outside of what's in the books. An amazing discovery from the last couple of years is that in addition to the quantum Hall states, which realize topological order and may have interesting phase transitions between different topological orders, there is actually lots of crystals in nature. There are some crystals in nature that seem to also be described by that Lagrangian that I gave you, which has, and they're lying somewhere in the region where there are dragons. So these are strongly coupled theories of very light anyons. So one famous mineral that you can buy on Amazon, it's called Herbert smithite. There is another one, I just didn't write it here, with this formula. And it just happens to have this cagomellary structure. It's a this kind of hexagonal lattice. And uh, well, I should call, yeah, let's call it hexagonal lattice. And it turns out that the low energy physics on this hexagonal lattice is very similar, if not identical, to some special cases of this Lagrangian. At low temperatures, of course. When you buy this mineral in Amazon, it's not going to come at 0 temperature. But people believe that at 0 temperature, it's going to be described by this Lagrangian. There is also a lot of numerical simulations of magnetic degrees of freedom on the Kagomel lattice. This is called the Kagomel lattice, some kind of hexagonal lattice. And there is a lot of indications from numerics from a couple of years ago that these theories do have dynamical anyons at low temperatures. And you see this kind of red lines. This is to indicate that there are some non-local correlations, like in topological order. So this is an exciting field where there is some interface with experiment also. Okay, that's how it looks like when you actually buy it, by the way, the Herbert smithite. So what do we know about this theory from the standpoint of pure theory? We can solve these theories when the integer n is huge or when the integer nf is huge. So when the number of species is very large or the magnetic flux through the solenoid is when the Chern-Simons coupling is very large, so the magnetic flux through the solenoids is very small, or when the number of species is very large, we can solve these theories. And I think both things are kind of intuitively clear if you have some experience with 3+1 dimensions, because if the integer n is very large, remember that the magnetic flux goes like Q over kappa, and kappa is linear in n. So when little n is very large, the magnetic flux is very small. And you don't really have to think about anyons anymore because the solenoid just leads to very small effects and you can just treat it in perturbation theory. So large n is perturbatively accessible. There is a scheme of doing perturbation theory when n is huge. And when the number of species is very large, you can also understand that the theory might be weakly coupled because in 3+1 dimensions, when you have lots of species of matter fields, the theory is infrared free. And something similar happens in 2+1 dimensions. It becomes very weakly coupled. These are still non-Landau-Ginzburg, but they're weakly coupled non-Landau-Ginzburg theories. So we know a lot about these theories with large little n or large nf because they are very weakly coupled non-Landau-Ginzburg theories. We can calculate the scaling dimensions, for instance, of the fermion bilinear, And the fermions behave almost like they're free fermions, but not quite. They're still anyons, but their scaling dimensions don't deviate very much from fermions. However, the interesting cases in nature have small values of little n and small values of the number of species, and there we need to make conjectures. We can use symmetries, anomalies, a renormalization group, monotonicity theorems, like the A theorem and C theorem, these kind of things, unitarity, and so on. So the interesting regimes are strongly coupled, unfortunately. And now we're going to go over the examples. There has been a huge amount of literature trying to make conjectures about the simplest possible examples. And I'm going to go over the conjectures now. Please stop me if there are any questions about the conjectures. Otherwise, I'll just chip one of them one by one, chipping them. Okay, let me see. There is no chirality. Yes, there is a question of whether there is a notion of chiral gauge theory because there is no chirality in anyons. It depends a little bit on semantics, but let's say if you mean by chirality the same thing that people mean in 4 dimensions, then you are correct. There is no chirality in these theories. But there is another notion of chirality that you can define, which has to do with time reversal invariance. So then the answer would be a little different. But if you just define chirality in the same way that we do in 4 dimensions, there is no chirality in 2 + 1 dimensions. Okay. Okay, we start going over the examples. So the first papers that made, shameless but brave conjectures in this field were written like 7 years ago by these people. These are the very first papers that analyze the simplest possible example. So they considered just one species of fermions, just one. So one electron, one electron. And so it's like, so it's equivalent to one spinor with 2 complex entries. So one Dirac spinor in 2 + 1 dimensions. That's the minimal amount of matter. And they made a conjecture about the case of n = 1. That case is very interesting. It's already non-trivial, and it describes the topological order. It describes no topological order here and some kind of almost trivial topological order here. Why am I saying trivial? Let me just go back a few slides. Remember that if n is 1, the topological spin is a half, but a half is a familiar number for the spin. So actually the wave functions are not multi-valued. They're just anti-symmetric. So that case is almost trivial. And actually this special case is Landau-Ginzburg because there isn't topological order here. Here you get 0, and here you get 1, which is not really anyons. N = 1 doesn't have real anyons. It's a trivial topological order. So these people noticed that this special case of an f = 1 and n = 1 may be Landau-Ginzburg at the end of the day. And it turns out that it is ordinary Landau-Ginzburg. The phase transition here is very familiar. And these people conjectured that it's the same as the phase transition between the normal phase and superfluid phase of helium. So it's a massless model. You don't even need anyons to describe it. It was known for a century. And it just describes the ordering into a superfluid. So sometimes we say that this model is dual to the superfluid transition, and it's an ordinary Landau-Ginzburg transition. So the contribution of that paper is that maybe they were brave enough to look at the simplest example. They realized that that example doesn't actually involve topological order, and they conjecture that it's the same as the phase transition of liquid helium. It's the O2 model. If you know a little bit about conformal field theory, it's the O2 Wilson-Fisher conformal field theory. And that's an interesting conjecture. We have some evidence for it. I view it as a very safe conjecture to make, to be honest, because there is sufficient evidence for it, in my opinion. Okay. And the first example, which is actually non-trivial, is when there are 2 species. And this is a theory that deserves to be called QED3, because 2 sets of fermions is the same amount of matter that we have in QED in 4 dimensions. We have the electron and the positron. So two sets of Dirac fermions in 2 + 1 dimensions deserves to be called QED3. It's also the simplest example that preserves time reversal symmetry for little n equals 1. So for general little n, it's a non-Landau-Ginzburg transition from topological order with n minus 2 units of flux to n units of flux. But if you just plug n equals 1, you get -1 here, 1 here. And this is time reversal invariant because you have 1 and -1, it's very symmetric. So for this reason, this theory with little n equals 1 and n f equals 2 deserves to be called QED3. So this is maybe the main challenge to understand what this theory does. This theory is also very close to what appears in this Kagome-Lattice and these minerals. So it's kind of the clear goalpost for what we should try to understand. So I spent a lot of time working on it in the last couple of years. We had some initial papers with some hints, but I think recently, just in the last couple of months, there were 2 papers, one with Shai Chester from Queen Mary, from Imperial College, and one paper by Ryan Thorngren, Thomas Dumitrescu, and Pierluigi Niro. Our 2 papers reached the exact same conclusion, and they appeared kind of independently, pretty much at the same time. And that's what we believe is going on in QED in 3 dimensions when the anyons become massless. We think that there is a gapped phase here with no topological order, a similar gapped phase here with no topological order. For the more advanced students here, I'll say that on this side there is an SPT, which is not topological order, but it's some symmetry protected topological phase. I don't have any time to explain what it is. It's just for the advanced student, a small comment. And then we believe that when the anyons are very light, something very strange happens. You get a nonlinear sigma model with target space, which is the 3-dimensional sphere with a theta angle. So the variables here are not anyons anymore, but it's just the arrow that sits on the 3-dimensional sphere. And you write a simple kinetic term for this arrow. In addition, because the 3-dimensional sphere has a third homotopy group, the Lagrangian for this arrow has a theta angle. And we put the theta angle to be exactly equal to pi at this point where the anyons are massless. So that's our conjecture. We believe that this is triggered by the condensation of a monopole. So that's the physical mechanism. I mean, of course, at some point, it's a little too advanced. I cannot explain everything from the beginning. I'm just giving you a flavor of what kind of things are happening. So the monopole condensation breaks isospin symmetry, and it leads to a theta angle. It's difficult to derive these claims, but and it's a conjecture, but I think it has a lot of circumstantial evidence, and we believe it's correct. And also, as I said, 2 papers reached the same conclusion independently. So that also is a little bit of a good sign. And we'll see if this is borne out in experiment or simulation at some point in the future. But that's the state of the art about QED3. About the other examples, we don't really know. So if you try to think, oh, something really bad happened with this slide, I'm very sorry. I'll repeat what it says. For other values of topological order or other values of the number of species, we don't really have a full picture. There are some few examples where where people made some sensible conjectures, like the ones I mentioned here. But more generally, we don't really know. We believe that if the number, as I said, if the number of species is very large, or if the topological order is very large, the topological order index is very large, it's just going to be a second order transition that's almost weakly coupled. So you might call it conformal window if you're familiar with 3 + 1 dimensional QCD. But when the number of species is very small, or the topological order index is very small, you might get some gapless modes like this S3 sigma model, or like in this example, there is the helium phase transition, which is described by an O2 sigma model. So you might get some Golson bosons here, but here we expect to get a direct phase transition between two non-trivial topological orders. So it's very similar to QCD in 3+1 dimensions, where there is symmetry breaking, the chiral symmetry breaking at strong coupling, and a conformal field theory at somewhat weaker coupling. So that's the big picture, and there are some concrete conjectures in some cases. So I just want to summarize and then discuss some open questions. The theory of anyons is not yet very developed. We know a little bit of here and there. We know that anyons can make condensates. So there could be a superfluid anyon, a superconductor anyon. There could be, I already showed you, non-Landau-Ginzburg transitions. Some of them are even weakly coupled, non-Landau-Ginzburg transitions. So we are sure that they exist. There are dualities. There is vast literature on generalizations of electric-magnetic duality to the theory of anyons. It's connected to the whole literature on quantum Hall phases, phase transitions between quantum Hall phases, and many things along those lines. That's actually the motivation for this whole subject, historically speaking. I didn't discuss supersymmetry, but there is vast literature on anyons with supersymmetry. You can look up some papers by Givion, Kutasov, and Aharoni. There is also vast literature on the connections with holography by Jian Yin. I can write it here. They made some, they have a significant amount of work, and also Minwala on the connections with holography. So some of these conjectures and about anyons are confirmed in simulations and even experiments, but most of it is open and unknown. And I just wanted to also finish for some questions for the students, the young generation. What should the young generation solve? So a big open question in the field, is there an S matrix? So when I mentioned this picture, I discussed the effects of anyons appearing from the vacuum. Maybe a more interesting question, about which we know even less, is what happens if anyons are light anyons, are the external states, and you just throw them and they scatter. So if you learned a little bit about scattering theory from Peskin, Schroeder, or Weinberg's book, you know scattering theory is a little subtle. You have to do the LSZ decomposition, you have to amputate the diagrams, and there are some physical conditions on when the S matrix even exists, and there are some infrared divergences, and so it's not clear if anyons can be scattered. We do not know the answer to this very basic question. Is there an S matrix for anyons? Does it obey crossing symmetry? Does it obey unitarity? These are questions for the students. It's not known. There are some simple examples where people looked at it recently, but the answer is certainly not known. The second question, what happens to the electric and magnetic field at the phase transition? So like this again, I'll go back many slides. I told you about what does an external charge produce in terms of the electric field and the magnetic field. That was at the very beginning of our discussion. But now imagine that you go through a phase transition that changes the topological order. What is going to happen if we put a nucleus with charge Q at the center of the sample at the phase transition? What kind of electric and magnetic fields would it produce, if any? We don't know the answer to this question. That's a very basic question that can be tested experimentally that we don't know the answer to. You can say that the question is, what is the response to an impurity, a charged impurity at the phase transition? This is a very interesting philosophical question. The whole point of Landau-Ginzburg was that we can detect phase transitions by taking a microscope, looking at the sample, and seeing if the spins are ordered or disordered, or if the liquid, or we're in a liquid phase where everything moves more or less everywhere, or we have a broken translational symmetry like in a solid. That was the whole insight of Landau-Ginzburg. The whole point of transitions between topological order is that you can use any microscope you want, but you won't see anything. So these phase transitions are pretty much defined by saying that nothing is essentially happening because there is no local experiment that it can detect topological order in the first place. So why would you go through a phase transition if nothing is changing locally? But I argued to you that you have to go through a phase transition. You have to change the topological order. But this brings a very interesting challenge to experiment. How to detect these phase transitions? What are we supposed to measure if there is no local order parameter? That's a very interesting question. Maybe we need to measure something non-local. Maybe we have to think about the theory of non-local order parameters. And that's actually my belief. What about non-abelian theories of anyons? I only discussed abelian theories of anyons. What about non-relativistic theories of anyons? What do we know about the scattering of anyons in non-relativistic theories? So these are all open questions for the students. I think I still have like 15 minutes if there are more questions to discuss. I see one long question. Maybe the person wants to say it just instead of me reading through it. It's very long, actually. Could this person maybe just ask the question directly, or should I read through it?
Yes, I can ask. I can try to ask the
Okay.
question. Can you hear me?
Yes.
So you were talking about that for the, I think it was for the n equals 2 flavors case. Some symmetry was lost because monopole condensation and thing, I think, and that makes you include a theta term. I think you mentioned something like that. So my
Yes.
question is, why does that happen? And by that I mean, usually when I think about the theta terms, I think of those as those terms should be there because respect all the symmetries, right? But in this case, initially you didn't have the theta term, but then something happened and that generated the term. So how does that work? Like why do you need to include the theta term after that monopole condensation thing?
This is it's a great question, but I view it as a very technical question. So I can recommend you to look at the papers if you have time or energy. Let me just go there. But more concretely, you add a theta term with a very specific value of theta, which is pi. And the value of pi doesn't break time reversal symmetry, and it doesn't break parity. Pi is like a very special value for a theta term that preserves all the symmetries. So if you're just very agnostic, you could say that if this nonlinear sigma model admits a theta term, I must think about, is it 0 or pi? Okay, because these two options preserve all the symmetries. And it turns out that only the option pi is consistent because of this keyword that I didn't explain here, you see, SPT. It turns out that to be able to generate a non-trivial symmetry-protected topological phase here, you need to add theta equals pi here. Otherwise, it's not consistent. So this is explained in detail in the paper, but the answer is kind of technical.
Okay,
There is a
thank you.
there is a less technical derivation in the paper of Dumitrescu, Nero, and Torngren. They show that this theta term arises from the way the gauge field interacts with the anyons. So there is some kind of geometric intuition for what they found some geometric intuition for how to get this theta term. We derived it through the SPT phase. Okay. Okay.
So I have a question about the first question for the students. I've read the paper from Witten in 1989, and he considered the conformal field theory in the Riemann space, and he claimed that if we have a Chern-Simons theory in the bulk, we can consider type of S matrix to consider. So my question is this part of the answer of this question, or we should consider more generalized question for the S matrix for anyons?
That's a good question. let me tell you what Witten did in that paper from 89. What Witten did in
John's
that paper from, yeah, that paper on
John's polynomial and
yeah, that's the paper on the
Chern-Simons
Jones
theory.
polynomials. So what Witten did is to calculate the amplitude, the phase that you get from braiding two anyons. He literally calculated this thing in that paper. He calculated the phase of braiding two anyons, doing this braid, and he called it an S matrix. He called it an S matrix because it reminded him of some maybe S matrix process, like some collision process. But the fact of the matter is what he did is for him the anyons were heavy, non-dynamical. He actually described them as Wilson lines in that paper, if you remember. So they were just heavy external particles. They were not fluctuating at all. And he just took them by hand and braided them, and he denoted the answer by an S matrix. What I'm talking about is the S matrix of dynamical anyons, which you actually scatter and you get a scattering amplitude of the cross-section. Witten doesn't, for Witten's S matrix is like some kinematical piece. It doesn't have the dynamical aspects of an S matrix, where there is S matrix is a function of incoming energy, angle, this kind of, he doesn't have any of that. He just described the process of braiding two anyons.
Okay, I see. Thank you.
Any other questions?
I just had one that Shinyu had partially answered in the chat. So I was just saying that like in string theory, I've seen a lot of, I guess it's like 60s Chern-Simons terms, like A wedge F, or A wedge F, I forget which. How similar is that to this 3D case? I mean, I assume it's pretty hard to write those terms in low dimension.
No, I think it's basically the same. It's basically the same thing. There is one difference in physics, which is that in string theory, these terms appear in supergravity, right?
Mhm.
So the objects that carry like, you know, Aronoff-Bohm fluxes and have funny statistics are typically some heavy d-branes. And they're like heavy non-dynamical objects for the most part.
I see.
So what we do in string theory is often very similar to this picture that is actually on the slides now, where you can think about the green line and the red line as d-branes. But string theory usually doesn't get into the regime where the objects that are anyons become dynamical.
Yeah.
That usually doesn't happen. You have to think about some situation where some d-brane becomes very light, and maybe then, but I don't know if people have tried.
Okay, perfect. Thank you. This presentation contained a lot of like good new ideas about the field
Okay,
theory side, so thank you.
Okay, thank you. Any more questions? Somebody's asking what is the symmetry of this PT? It's an SPT for some. I'll write it down in the chat. This is the global form of which has an SPT. That's for maybe the experts. Any other questions?
Is there a way to represent those anyons by some other system not having any gauge field inside? Like just some fun nanoparticles with given statistics?
Well, I think in this formalism, let me just go to that slide. In this form, oh, where is that? Sorry, I'm looking for something concrete. So yeah, in this formalism where we have a wave function of n coordinates, and we just say that the wave function has funny, you know, monodromies, that it lives on a multi-sheeted cover of configuration space. In that formalism, we don't have a gauge field. But here the anyons are heavy. They're not created or annihilated from the vacuum, and they're just probe. They're kind of like heavy nuclei that move around and sit in some wave function and have some wave function. So in this formalism, we don't need a gauge field, but I think if the anyons become dynamical and they're light, I think you need a gauge field. I've never seen a formalism that doesn't have a gauge field, to be honest.
I see. I see. Yeah, I was more thinking of the latter case when they become dynamical. Like
Yeah,
if you
I've
can
not,
achieve that without flux attachment, that's what I'm asking. Yes.
I've never seen, I've never seen a formalism that just has flux attachment and then you forget about the gauge field. I think flux attachment is just a qualitative idea that becomes precise when the anyons are heavy. I don't know how rigorous it can be done. It can be made when the anyons are light. I just don't know if it's
Okay.
even possible.
Thanks.
There is no one for somebody's asking. There is no one form symmetry in that business. You can take a look at the paper. It's explained